last video, we introduced the concept of a sequence as well as the associated concept of a series. So over the course of the next two videos, we're going to discuss specific types of sequences. So there are special sequences that are marked by functions that are defined in the same kind of way. So an arithmetic sequence is a sequence that has a function structured in a very specific way. So every sequence that is considered arithmetic will have a function rule that's structured in the same way. So how will these rules be structured? So an arithmetic sequence is a sequence in which the terms progress in a linear fashion, which is another way of saying each term differs from the previous one by addition or subtraction of a fixed value. So we'll start with a particular term, we'll call A1. The next term will consist of A1 plus some value that we call D. The next term will be A1 plus 2D. The next term will be A1 plus 3D. And then so on and so forth for any term in the sequence. So the value A1 is going to be the first element, the first term, and D is referred to as the common difference of the sequence. So the value D can be defined as D is equal to A sub n plus 1 minus A sub n for any pair of consecutive terms. In other words, if you were to take any pair of consecutive terms and take the latter minus the former, you'll see this common difference, this value of D. The difference between any pair of successive terms, consecutive terms, is going to be the same, and this is what we define as the common difference of D. So the nth term, the formula, in other words, for defining an arithmetic sequence, can actually be written in two ways. So if we want a non-recursive sequence, in other words, one where we can just find any term individually in the sequence without needing the terms before it, then our nth term is defined as A sub n is equal to A sub 1, whatever that happens to be, plus n minus 1 times the common difference of D. Once we have the actual value for A sub 1 and the actual value for D, typically we can simplify this and write it in a little bit more concise way. But if the goal is to actually structure the nth term, find the formula for that, we plug in A1, we plug in D, and we write the formula that results. Now, because each term in the sequence is also dependent on A1, and then we build from there, we can also define the sequence recursively. So recursively speaking, we have A1 must be given, and then each term after that is defined in terms of the term that preceded it. So the nth term is defined as the previous term, the preceding term, A sub n minus 1, plus our common difference of D. And this rule is going to apply for any value of n that is greater than or equal to 2. So in other words, we need to have the first term given, but past that we can build on that first term by just adding on that common difference to any term to get the next term. So if we wanted the second term, for instance, A sub 2 would be A sub 2 minus 1, in other words, A sub 1, plus our common difference. A sub 3 would be A sub 3 minus 1, which would be A sub 2, plus that common difference. And so if we have any particular term in the sequence, we add on that common difference and we'll get the next term in the sequence. So both of these are considered acceptable ways to define an arithmetic sequence. It's just going to depend on what kind of formula we want. So let's determine whether the following sequences would meet the requirements to be defined as arithmetic. And if so, we want to find the common difference. So how do we know if a sequence is arithmetic? Well, again, the idea is that all of the terms progress in a linear fashion, which means if we look at the difference between any two consecutive terms, it's the same difference for any pair of consecutive terms. So for A sub 1 to A sub 2, what is the common difference in this case? Well, A sub 2 minus A sub 1, the difference between those consecutive terms, is going to be 25 minus 35, which comes out to negative 10. So the difference between the second term and the first term is negative 10. Now that difference needs to be the same for every consecutive pair in order to say that this sequence is arithmetic. So what about a sub 3 minus a sub 2, the next pair? Well, that's going to be 15 minus 25. And sure enough, 15 minus 25 is also negative 10. Okay, what about the next pair? So a sub 4 minus a sub 3. Well, a sub 4 is going to be 5. So 5 minus 15, also negative 10. And then we've also been given a sub 5, so a sub 5 minus a sub 4. That's going to be negative 5 minus 5, which also gives us negative 10. And the ellipsis here tells us that we've established a pattern and we can assume that that pattern continues indefinitely. So because the difference between each consecutive pair of terms is going to be the same, then we can say that this sequence is arithmetic. And the common difference of D is going to be that common value we have that is the difference between each pair of consecutive terms. So in this case, D is going to be negative 10. Okay, let's look at another sequence. So is this sequence an arithmetic sequence? Well, again, we're going to check in the same way. We want to see how do we progress from one term to another, specifically as we compare pairs of consecutive terms. So A2 minus A1, if we take the difference between those two, that's going to be 5 minus 1, which is 4. So in order for this sequence to be arithmetic, we need to have a difference of 4 between every pair of consecutive terms. So what about the third and the second term? Well, a sub 3 is going to be 10, and then a sub 2 is 5. So 10 minus 5 is going to be 5, and automatically we don't need to go any further because notice these two values don't match. The difference between the first two terms is 4, but there's a larger difference between the second pair of terms. So because this difference is not consistent for every pair of terms, we would say that this is not an arithmetic sequence. So it does not meet the requirement that we have for it to be an arithmetic sequence. So based on this idea of what an arithmetic sequence is, let's practice actually writing the rule for an arithmetic sequence. So we want to write the first 5 terms of the sequence as described, and then we want to write both a recursive and a non-recursive formula that will define this sequence. In other words, we want to write the nth term, but we want to write it in a recursive manner and we want to write it in a non-recursive manner. So suppose we have an arithmetic sequence where the first term is negative 5 and we have a common difference of 4. What does this common difference of 4 mean? It means if we start with a value of negative 5, then every additional term in the sequence is going to be 4 units away from the preceding term. So the first term, a sub 1, is going to be negative 5. A sub 2 will take our first term, negative 5, and we'll add on that common difference of 4, which takes us to negative 1. Now a sub 3 can be determined in a couple of different ways. We'll think of it as negative 5 plus 2 times our common difference. Based on the definition we have for an arithmetic sequence, that's how we would determine that value. So negative 5 plus 2 times 4, which is 8, is going to give us 3. And then a sub 4 is going to take our first term plus 3 times our common difference. So 3 times 4 is going to be 12. Negative 5 plus 12 is going to be 7. And then a sub 5 is going to take our first term plus 4 times our common difference. And so that's going to be negative 5 plus 16, which will be 11. So from a definition standpoint, this would be how we calculate each individual term. The progression in a linear fashion is indicated by the fact that we're adding on one additional unit of that common difference every time we go from one term to another. But the idea of recursion is very much present. Rather than thinking of starting with a sub 1 each time, another way of thinking of generating these terms is start with a sub 1, we'll add the common difference to get to the next term. If you then were to start with this next term and add the common difference again, you get to the next term, and then add it again, you get to the next term, and the next term, and so on and so forth. So that's the idea behind the recursion here. So for the recursive formula, we need to indicate first what is A1. That's going to tell us where the sequence starts. We need to know where it starts in order to know how we're going to build. And then the nth term is going to be defined as the term that preceded it, which would be a sub n minus 1, plus our common difference. So plus 4, and this rule applies for any values of n greater than or equal to 2. So we know that our sequence starts at -5, and in order to generate any particular term, we take the preceding term and we add on the common difference of 4. Now the non-recursive formula is going to be given by our first term, a sub 1, plus n minus 1 times d. So that's going to be the formula representing any arithmetic sequence. So our value of a sub 1 is -5, and our value of d is 4. So that means a sub n is going to be -5 plus n minus 1 times 4. Now keep in mind n is truly the variable. So anytime we want to generate a particular term, say we want to generate the 50th term, we're going to sub in a 50 in place of n and then simplify the expression. Now we can technically leave it in that form if we want, but there's potentially a cleaner way to write this if we distribute the 4 and then go from there. So if we distribute the 4, we're going to have -5 plus 4 times n minus 4, so 4 times -1 is -4. And if we simplify that, combine those like terms, -5 combines with -4, then we have the formula 4n minus 9. So that's going to be the simplest form of the formula that generates our nth term. And again, the benefit of having a non-recursive formula is we can find any term in the sequence without needing the terms before it. So if we use a recursive formula, suppose we wanted the 50th term. Well, the 50th term is going to take the 49th term and add on 4. But in order to have the 49th term, we need the 48th term, and then we add on 4. So a recursive formula requires that we have all the preceding terms to build up to any specific term, whereas the non-recursive formula only requires us knowing which term in the sequence we want, what its position is, and then we can just plug in the location, and that'll help us find the individual term. So let's look at a slightly more difficult example. Not every value of d and not every value of a term in the sequence, our starting term, is going to be an integer. In some cases, we may have fractional values. That doesn't necessarily mean we're not looking at something arithmetic. It just means we're starting with a fractional value and we're building based on an additional fractional value. So in this case, if we want to write the first 5 terms of this sequence, where our first term is 2/3 and our common difference is -1/2, then we can do so accordingly. So in this case, because our common difference is negative, that means our terms are going to get smaller as we progress through the sequence. So a sub 2 is going to be 2/3 plus -1/2. Otherwise, we can just think of it as subtracting 1/2. If we want, we can do that in the calculator, which will save some time. So 2/3 minus 1/2, and then we convert that to a fraction, and that's going to give us 1/6. Now suppose you didn't have a calculator or you wanted to work this out in a different way. You would have to get your common denominator, of course, and then you combine and reduce whatever fraction you end up with. So a sub 3, based on the definition for an arithmetic sequence, would take our first term plus 2 times our common difference. So in this case, 2 times negative 1/2. So in the most formal sense, this would be the way we would calculate the third term. So 2/3 plus 2 times negative 1/2. And there we go. And if we convert that to a fraction, we get negative 1/3. So notice we've gotten smaller again. Now we're in the negative numbers. And since we're continuing to decrease, we'll get more and more negative over time. So what about a sub 4? Well, a sub 4 is going to take our first term plus 3 times our common difference. So that's going to be 2/3 plus 3 times negative 1/2. And again, we can convert that to a fraction, and that's going to give us negative 5/6. And then the fifth term in the sequence is going to take our first term, and we're going to add on 4 times our common difference. Oops. Let's try that again. So 2/3 plus 4 times negative 1/2, and then convert it back to a fraction, and we get negative 4/3. And so those would be the first 5 terms in our sequence. And keep in mind, if we were to look at any pair further out minus the previous term and subtract, we end up with that common difference of negative 1/2. So every pair is separated by a difference of negative 1/2, which is the hallmark of an arithmetic sequence. So a recursive formula generating this particular sequence would require us knowing, again, our first term, where we're starting. In this case, the first term is going to be 2/3. And we know that every individual term in the sequence is going to take the preceding term, and from that term, we're going to subtract 1/2. So you could write it as plus negative 1/2, or just minus 1/2 is a little bit better way to write it. And that rule is going to apply for all values of n greater than or equal to 2. And then if we want our non-recursive formula, that's going to be a sub n is equal to our first term, which is 2/3, plus n minus 1 times our common difference, which in this case is negative 1/2. So let's clean this one up. Same strategy. We want to distribute that negative 1/2. Now be very careful when you do that. So we have 2/3. Now negative 1/2 times n is going to be negative 1/2 n. And then when we multiply the negative 1/2 by negative 1, that's going to become an addition. So plus 1/2. And so if we write the variable term first, that's going to be negative 1/2 n. And then we combine the fractions, combine those like terms. So that's going to be 2/3 plus 1/2. And then we convert that to a fraction, and we get 7/6. So plus 7/6. So for any specific term in the sequence, if we know the location of the term, we can sub it into this formula, and this will give us the value of the actual term. So let's look at an applied example where our situation is modeled by an arithmetic sequence. Okay, so a park ranger in Everglades National Park measures the water level in one region of the park for a 5-day period during a drought. Okay, so we have our days, 1, 2, 3, 4, 5, and we have the water level in inches. And notice it's going down. There's a drought, so the water level is going down. So the first thing we want to do, we want to show that this data follows a linear progression. What does that mean? Well, essentially we want to know what's the difference between each of these values, and if this is a linear progression, then we'll find that the difference between each value is a constant number. So what would it take to go from the level on the first day to 53.2? What happens to progress from one to the other? Well, if we go from 54 to 53.2, 53.2 minus 54. The further out term minus the preceding term is going to be negative 0.8. Okay, well the next value we have is 52.4. So what's the difference to take us from one to the next? So 52.4 minus 53.2. Notice that's also negative 0.8. So we have a constant difference so far. Okay, check the next value. So 51.6, we want the difference between that and the preceding term. So 51.6 minus 52.4, oops, 52.4, there we go. And we get negative 0.8. And then as we go to the last term, 50.8, 50.8 minus 51.6 is also negative 0.8. So because each value is smaller by 8/10 from the value that precedes it, that's our indication that we have a linear progression. In other words, if we were to graph these individual values, they would occur in a straight line from one another. There wouldn't be any deviation from that line. So the next thing we want to do is write an expression for the nth term of this sequence, noting that the terms progress in a linear fashion. Hence, this represents an arithmetic sequence where n represents the day number. So this is an arithmetic sequence. We just showed that because there is a common difference. So this value, negative 0.8, is our common difference. So our formula is going to take the starting value, a sub 1, the value that our sequence starts at, so 54.0, and we're going to add on n minus 1 times our common difference, which in this case is negative 0.8. So let's clean that up a little bit. So again, distribute negative 0.8. So that's going to be 54.0. Negative 0.8 times n is negative 0.8n, so we're subtracting. And then negative 0.8 times negative 1, that turns positive. So plus 0.8. And if we take that one step further, combine our like terms, we have negative 0.8n, and then 54 plus 0.8 is going to be positive 54.8. So this is going to be the formula representing the value, in this case the water level, on any particular day, assuming that day is represented by the value n. So based on the information we want to have so far and based on the trend that we see, we want to predict the water level on day 30, assuming that the trend continues. In other words, we're progressing in a linear fashion so far. Suppose we continue to do so. What will the water level be on day 30? So in other words, we want to find the value of a sub 30. 30 in this case is going to be our value for n, and so we want to find the 30th term in the sequence represented by this data. And so we can determine that directly based on this nth term that we just found. So that's going to be negative 0.8 times 30 plus 54.8. And so we can plug that into the calculator. So negative 0.8 times 30 plus 54.8. And we get a value of 30.8. And of course, since this is an applied problem, we want to indicate the unit. Well, we're talking about the water level on a particular day, and we know the data is given in inches, so this will be 30 inches. So after 30 days, if this trend that we see were to continue, we will have gone from a 54-inch water level down to a 30.8-inch water level. Okay, so what we know about defining the nth term can actually be used in a variety of different ways. So we can define pretty much anything we need about the sequence as long as we can find information about our first term and about our common difference. So in general, defining the nth term of our sequence requires knowledge of a sub 1, our first term, and d, our common difference. And defining any specific term also depends on the value of n, which is our term number. So different scenarios, different combinations of information may present us with different combinations of these values. And as long as we understand how the values are related, then we can pretty much determine anything we need from anything that we have. And again, we always fall back on the fact that our formula is structured in such a way so that the nth term, any specific term in the sequence, is defined as the first term plus n minus 1 times our common difference. Everything comes back to this formula. So depending on what information we're given, we can use that given information to structure our formula and then interpret accordingly. So for example, we want to find the 9th term of the arithmetic sequence in which a1 is equal to -4 and a sub 22 is equal to 164. So finding the 9th term, what does that mean? Well, we would plug in 9 to our formula and then we would go from there. But we don't have our formula. So finding the 9th term requires that we have the formula. So what do we actually know? Well, a sub n in general will be our unknown. We know a sub 1, we've been given that that's -4. And we know we're going to take -4 and we're going to add on n minus 1 for whatever n is times d. So we know a sub 1. N is our variable in any situation. In this case, the value of n we want is going to be 9. But what we don't know is the value of d. We do not know what the value of d is in this case. Okay, but based on the structure we have, based on the fact that we know a sub 1, and also based on the fact that we know another value, we actually have enough information to solve for d. So we've used this piece of information. We've been able to sub in the value for a sub 1. Here's how we're going to use the next piece of information. I want to structure this statement based on my knowledge of the fact that a sub 22 is equal to 164. So if I were to sub in these values to the formula I have right here, what would I get? Well, I know that a sub 22 is equal to a sub 1, which we know is -4, plus n minus 1. Well, what is n in this case? N is 22. So 22 minus 1 times d, which again, we don't yet know. But what we also know on top of the fact that this would be the formula generating a sub 22, we also know that all of this will have to be equal to 164 because that is the value of a sub 22. And so essentially what we now have is an equation. We have an equation that has one variable. And so if we can isolate this variable, then we can solve for it and we'll have a formula. We'll have the formula that we need. So I would go ahead and simplify this. We don't actually need to distribute that d because this is now just a fixed value. So this is going to be -4 plus 21 times d. And we know this is equal to 164 because that was the value of the 22nd term in our sequence. So now we just want to isolate d, and that will give us the common difference for our formula. So I'm going to add the -4, move it over. So we have 21d is equal to 164 plus 4, which will be 168. And so if I divide both sides by 21, then I'll get my value of d. So d is going to be 168 divided by 21, and that's going to give us the value of 8. So in other words, each pair of consecutive terms is separated by a value of 8. To go from one term to the next, we increase by 8 each time. And it does make sense because we start with a lower value, and as we progress in the sequence, we end up with higher values. So based on this, we now know the formula for the nth term. So based on that, the formula for the nth term is going to take a sub 1, which we were given. We know that's -4, plus n minus 1, because we're writing the formula for the nth term. And then that is now going to be multiplied by our common difference of 8. So this formula, and then variations of that formula, assuming we wanted to simplify everything, this is going to generate any term we want in our sequence. So we're not quite done, because what do we want? We want the 9th term. So in other words, we want to determine what would the value be when n is equal to 9. So we want to find a sub 9. Well, we can find that value by substituting a 9 in place of n. So this is going to be negative 4 plus 9 minus 1 times 8. So that's going to be negative 4 plus 8 times 8. Well, 8 times 8 is 64. Negative 4 plus 64 is going to be 60. So based on the information we were given, based on finding D, and then structuring our formula, our nth term, we were able to determine that a sub 9 would have a value of 60. Does this make sense in the context of the problem? Well, our first term is negative 4. Our terms are growing by a difference of 8 each time. And we know by the time we get to the 22nd term, we're at 164. So at least it makes sense that we have a value that would be between negative 4 and 164. Okay, let's try a slightly different kind of problem. And again, the idea is think about how all the different components are related to one another in the sequence that we have. Okay. So now we want to find the number of terms in this finite sequence. Okay, well, why does this apply right here? How do we know we can actually work this problem? Well, we can determine that this is an arithmetic sequence. So notice to go from 7 to 3, we decrease by 4. To go from 3 to negative 1, we decrease by 4. To go from negative 1 to negative 5, we decrease by 4. So there is a common difference involved in this case. We want to determine, based on our information of how an arithmetic sequence is structured, how many terms are actually in the sequence that's been written down. Normally a sequence continues forever. This is a finite sequence that starts with 7 and then terminates at negative 113. So we literally could list out all the numbers from negative 5 to negative 113, but that is not a very efficient way to solve a problem. So we want the number of terms. So the number of terms in this case is going to be n. We want to know what's the value of n by the time we get out to negative 113. So this is the first term. This is the nth term. We want to know what is n in this case. So again, we want to fall back on what we know about an arithmetic sequence. And what we know about an arithmetic sequence is how we write the formula for it. So the nth term is always given by a sub 1, which in this case is 7, plus n minus 1 times d. Now we just determined to go from one term to the next, we decrease by 4 each time, so d is going to be negative 4. Okay, so we can clean this up if we want, or we can just leave it as is, either way. So we want to know what is n in such a way that the nth term is going to be negative 113. So in other words, if all of this, if the formula for our sequence evaluates to negative 113, if the value, the term is negative 113, well, what's the associated term number? That's the question we're asking. So we're going to take our formula, where n is our unknown, because again, we're looking for the term number, the number of terms, and we're going to set it equal to the value of the nth term, which is negative 113. And again, we have an equation with one variable, and so we can solve for that variable. And again, you can go ahead and distribute if you want. There's a bunch of different ways to simplify something like this. It's really just personal preference. I probably would distribute just so I have individual terms and I don't see any parentheses. So if we distribute, we have 7 minus 4n plus 4 is equal to negative 113. Okay, now the two constants, we'll move those over so we can isolate n. So that's going to be negative 113, and then we're subtracting 4, and we're also subtracting 7 to move both of those constants over. So that's going to leave us with negative 4n is equal to negative 124. And so if we divide by that negative 4, divide by negative 4, we end up with n is equal to 31. So in other words, to go from 7 to negative 113, progressing in this fashion where we decrease by 4 each time, we would have to go out 31 terms in order to get to this particular term. Now just a heads up, with something like n, where we're solving for something like n, there are very specific restrictions on what n can be. N must be a positive integer. N is our term number. N is the input for our formula that we're using to calculate the terms in the sequence. So the term number is always going to be a whole number, and it's always going to be something that starts at 1 and then continues from there. So if you were to find a fractional value of n, automatically that's a red flag, you've done something wrong. If you were to find a negative value for n, again, a red flag that you've done something wrong, because n has a very specific meaning in the context of a sequence. It can only be a positive integer. So here, the 31 does make sense. Okay, let's try one additional problem. This one is kind of similar to the first one we worked, where we solved for the formula and then we found a term, but we've been given slightly different information. So this is going to kind of combine the two that we've done in terms of how we structure our information. So we have an arithmetic sequence in which a sub 15 is going to be 49 and a sub 27 is 85, and we want the 500th term in the sequence. Okay, so automatically, I know we don't want to make a list all the way out to 500 terms, so we're going to have to solve for our formula for a sub n and then evaluate it with an input of 500. Now this particular problem is a little bit more challenging than the first two problems, the ones we just worked, because notice we haven't been given our starting term. In both of the examples we just looked at, we were given a sub 1, which gives us a good place to start in generating our nth term. So we have not been given a sub 1 in this case. And notice we also don't know what the common difference is. All we know is that if we go from the 15th to the 27th term, then we've made it from 49 to 85. But that's not enough to immediately see what the common difference is. So there's actually two things that are unknown in this case that we will need in order to generate the nth term. So based on how the nth term is structured though, every term is structured in the form a sub 1 plus n minus 1 times d. Well, what does that look like for these two terms? In other words, when n is 15 and when n is 27. Well, for a sub 15, this is what we know. For a sub 15, we know that it's going to be our first term, whatever that is, we don't know what it is right now, plus n, which is 15, minus 1, times d, which again, we don't know. That's still unknown. But we know that whenever we evaluate whatever this is, it's going to evaluate and simplify to 49. So this is now going to give us an equation, but unfortunately it's an equation that still has two variables, so we can't directly solve for the value of 1. However, we do have another term in the sequence that we can interpret in the same way. So we know that a sub 27 would be equal to our first term, again, unknown, plus 27 minus 1 times d, again, unknown. And whatever all of that is, it evaluates to 85. And so what we now have is a system of equations. We have two equations, each containing two variables. And as long as we have two equations, we can solve for two variables. So now it's just a matter of solving that system of equations. Okay, so let's clean these up just a little bit. So we have A1 plus 14D is equal to 49. That's our first equation. And we also have A1 plus 26D is equal to 85. Now we have a variety of options for solving a system of equations like this. A1 would be easy to isolate in either situation, so we could do substitution. We could pick one of the equations and isolate A1 and then substitute in the other equation. That's an option. We could also use elimination. If we can get terms to be equal and opposite to match up, we could do elimination. That's an option as well. Or we could write a matrix, and we could solve this using a matrix. If we can reduce our matrix using the graphing calculator, then we can also solve for our variables in that way. And ultimately, it's not going to matter which approach you take. Just pick one and go with it. So I'm actually going to use elimination because I notice I have these terms lining up and it would be easy to cancel them out. All that we need is for one of them to be negative. So if we have a positive A1 and then we subtract everything in the next equation, then we can get those two terms to cancel out and we can eliminate them. So if I subtract everything, my A1s are going to go away, and then I'm going to have 14D minus 26D, which would give me negative 12D. And then on the other side, I have 49 minus 85, because keep in mind, everything is subtracted. And so that's going to give me negative 36. So if I divide by negative 12, negative 36 divided by negative 12 is going to be 3. Now, how do we know if this D makes sense? Well, the same restrictions that we have here do not apply to D. D can be a positive number, it can be a negative number, it can be integer, it can have a fraction attached to it. D can be pretty much anything we want. We looked at an example where D was negative 1/2. There are no restrictions on D the way there are on something like N. But the fact that our terms are whole numbers indicates that more than likely D is probably a whole number as well. But again, that's not necessarily a guarantee. We could progress by a fractional value and make it to two whole numbers. It's really just going to depend. But as long as we used an appropriate technique to solve, there's no reason to think we'd end up with the wrong value. So based on knowing the value for D, well, now we can go pick one of our equations and sub in that value and then solve for A1. Doesn't matter which one you use, I'm just going to use the first one because the numbers are smaller. So we know that A1 plus 14 times D, which we determined is 3, is going to be equal to 49. So based on that, A1 is going to be 49 minus 14 times 3, which is 7. So that tells us our starting term in this sequence, which we were not given, is the term 7. So if we know our A1 and we know our value for D, then we can write the nth term. So the nth term is going to be 7, which is A1, plus n minus 1 times D, which is 3. Now our goal, the ultimate goal, was to find the 500th term. So now that we have the nth term, we can find the 500th term. So I'm just going to sub in 500 in place of n. So 500 minus 1 times 3. And we can evaluate that all in the calculator if we so choose. So 7 plus 500 minus 1 times 3. And that's going to give us 1,504. Does this value make sense? Well, we know that our terms are increasing. If we go from the 15th term at 49 and into the 27th term at 85, the terms are continuing to increase, so our terms increased from there. And if we're all the way out at the 500th term, it makes sense that it'd be quite a bit larger than the two terms that we were given. So the answer at least makes sense in the context of this problem. So now that we've looked at several different situations involving an arithmetic sequence, let's talk about an arithmetic series. So if you recall, a series is just what results when we take the terms in a sequence and we add them up. So we have two different types of series. We have an infinite series, which means literally adding up every term in the sequence, which in some cases would be difficult to do. And then we also have a finite series, which means we're only adding up some of the terms. We're only adding up the first n terms. So if we add up the first n terms in an arithmetic sequence, we have what's referred to as the nth partial sum of the sequence. And the notation for the nth partial sum is going to be capital S with a subscript of n. So n will have an actual value when we're actually evaluating a particular series. Suppose we wanted the first 100 terms in the series, well, we would add up 100 and n would be 100. Now, adding up large number of terms can be tedious. What if we wanted to add up 1,000 terms or 1,000,000 terms? Doing that by hand would be very difficult. But fortunately, there is a formula that allows us to essentially take a shortcut. Rather than having to manually add up a bunch of numbers, there is a formula that will tell us what the value of the series is going to be. So if we want the nth partial sum for some value of n, it's currently unknown, but we'll know what it is in an actual problem, the value is going to be n divided by 2 times a sub 1 plus a sub n. That will be the value of the series. Now, this is just for a finite arithmetic series. What happens if we have an infinite arithmetic series? Well, an infinite arithmetic series would diverge. We can't actually evaluate the sum of infinitely many terms structured in this way. Either our terms continue to get larger and larger and larger over time, or they continue to get more and more and more negative over time. So if you continue to just add up terms that are getting bigger in either direction, you're never going to get to an actual value. As you continue to add on more terms, the sum continues to grow. So an infinite arithmetic series diverges. You cannot actually find a fixed value for it. It's either going to become infinite in the positive direction, or it's going to become infinite in the negative direction. So the only type of series we can define in terms of something that's arithmetic is going to be a finite series. And whatever this value comes out to based on our value of n, and based on knowing where our sequence starts and then where it ends, in terms of what the value of n is, this is going to be the value of the sum if we were to add up all of those terms one by one. So keep in mind, this doesn't have to be a whole number. If we're adding up terms that are fractional, we may end up with a fractional sum. Also, suppose n is an odd number, something like, I don't know, 5. Well, 5 divided by 2, automatically we introduce a fraction into the problem. So don't assume automatically that every sum is going to come out to a whole number, because that's not necessarily going to be the case. It's really just going to depend on the sum that we're looking at and the sequence that it resulted from. So let's try a few examples evaluating these finite series. Again, just given different kinds of information. So first example, we want to find the sum of the first 50 terms of this sequence, 2, 4, 6, 8, 10, and so on and so forth. So in this case, n is going to be 50, and if we want the sum of the first 50 terms, then we are looking for s sub 50. That's what we're trying to determine. Well, we know our partial sum. The formula for our partial sum is going to take our value for n, which in this case is 50. We're going to divide it by 2, and we're going to multiply that value by our first term in the sequence, which in this case is 2, plus the nth term. Well, n is 50 in this case, so plus the 50th term. So the question is, what is the 50th term? We have everything we need except the 50th term. Well, first off, we know this is arithmetic because we're increasing by a value of 2 each time, so the common difference is 2. But we've only got 5 terms. We need 50 terms in order to get out to the specific term that we want. So just like with the previous problems that we worked, go back to the formula for the sequence. How is the sequence defined? If we know how the sequence is defined and we can write the nth term, then we can find any specific term. In this case, we want the 50th term. If we know the nth term, we can find it. So let's write the formula for the nth term. So a sub n is going to take the first term, which is 2, and we're going to add on n minus 1 times our common difference. Well, we're increasing by 2 with each pair of consecutive terms, so that means our common difference is going to be 2. So based on this formula, we want to know what is a sub 50. So a sub 50 is going to be 2 plus 50 minus 1 times 2. And if we simplify that down, that's going to be 2 plus 50 minus 1 times 2, and that comes out to 100. Now that's not necessarily surprising. Clearly there's a pattern here. You could think of these as just being even integers. So the 50th even integer is going to be 100. Okay, so that's going to be the value that then goes into the formula for our partial sum. So we can go ahead and simplify the 50 over 2. That's going to be 25. And then we have the first term plus the 50th term, which is 100. And so if we simplify all of that down, that's going to be 25 times 2 plus 100, and that comes out to 2,550. So what does this represent? This represents the value we would get if we were to add up all of these numbers, continuing the pattern, all the way up to the number 100. It makes sense that it's a big number because, again, we're adding up terms. Even though the terms start out small, they continue to grow, so we continue to add on larger and larger and larger numbers. And so when we add up everything all the way up to 100, then we get a value of 2,550. Okay, let's try another one. Same idea, same directions, different kind of information is given. So we want to find this particular sum. Now, first off, we know this is arithmetic. How do we know this is arithmetic? Well, look at the terms. We've added up terms. How do they differ from one another? Well, we decrease by 0.5, decrease by another 0.5, decrease by 0.5, and so on and so forth. Okay, so we continue to decrease, and we're adding up all the terms that progress in that fashion until we get to negative 30.5. But the question is, if we've made it out to this term, well, what is the value of n associated with that term? How many terms do we actually have? How many are we adding up? Because that's going to be important in evaluating our sum. We need to know how many terms we're adding up. So we want s sub n, some partial sum, and we know it's going to be n divided by 2, n is unknown, times our first term, which is 5, plus our last term, which is negative 30.5. So I can just write that as a subtraction. So the question then is, what is n? We need to know what n is in this case in order to evaluate this partial sum. So again, go back to the formula. What is the formula for the nth term? Well, the nth term in this case is going to be a sub 1, which is 5, plus n minus 1 times d. Well, what is d? Well, again, we noted that we're decreasing by 0.5 each time, so d is negative 0.5. So how are we going to use that in this case? Well, remember, n is what we want to solve for. We know what the nth term is in terms of where we're ending this sequence. We know that when we get out to our value of n, that all of this is going to evaluate to negative 30.5. So the question we're answering is, what value of n would allow us to evaluate this to a value of negative 30.5? So we're just solving for n such that all of this is equal to negative 30.5. So let's go ahead and distribute, clean things up, because the goal is to isolate our n. So we have 5 minus 0.5n plus 0.5, and all of that is equal to negative 30.5. Okay, so isolate our n term, move these other two terms, the constants, over to the other side. So on the other side we have negative 30.5 minus 5 minus 0.5. And that's going to give us negative 36. So negative 0.5n is equal to negative 36. And if we divide by negative 0.5, initially it looks like we might have a problem because we're dividing by something fractional, but that's not the case. So we're dividing by negative 0.5, and we get a positive integer. Remember, n should be a positive integer. So in this case, n is 72. So what that tells us is that if we've added up all of these terms in this sequence and we've made it all the way out to negative 30.5, then we've gone out 72 terms. So what we're actually evaluating in this case is the 70th partial sum, or excuse me, not the 70th, the 72nd partial sum. Here we go. So I'm going to plug in a 72 in place of n. That is then divided by 2. And I'm multiplying that by 5 minus 30.5. Okay, so we can simplify a little bit at a time, or we can just plug all of that in at the same time. So 72 over 2 is multiplied by 5 minus 30.5. And that's going to come out to negative 918. Is it a problem that this is negative? No. It makes sense that it's negative because our values continue to decrease. So we're going to get down to 0 pretty quickly, and then suddenly we're adding on larger and larger and larger negative numbers, all the way out to negative 30.5. So it does make sense that adding up those terms would result in a negative sum. Okay. So let's look at this last sum. Now this sum is given in summation notation. So we looked at this notation in the last video. We discussed what this notation means. This notation can also be used when we're talking about something like an arithmetic sequence. So this, think of this as the formula for the nth term. So we're saying that a sub n is equal to 3n plus 5. Now we've used I instead of n, but the idea is the same. So each individual term is defined by subbing in the term number, multiplying by 3, and then adding 5. So what does this actually represent? Well, it represents taking this formula and subbing in 1, and then 2, and then 3, all the way out to 60. So if we were to try to evaluate this by hand, this is essentially what we're doing. We've got 3 times 1 plus 5 plus 3 times 2 plus 5 plus dot 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 all the way out to the 60th term, which would be 3 times 60 plus 5. Well, you'll notice all of these are going to be positive numbers, so we're adding up bigger and bigger and bigger positive numbers. So this sum is going to be pretty large. Okay, but what does this actually look like? What are we actually adding up? Well, the first value, 3 times 1 plus 5, would be 8. And then 3 times 2 plus 5, that would be 6 plus 5, which is 11. So on and so forth until we get to 3 times 60, which is 180, plus 5, which is 185. So we're adding up this particular sum. Well, based on writing it in this expanded form, we know exactly what we need to know in order to find this partial sum. What does this actually represent? This is the 60th partial sum. We're adding up the first 60 terms. And we know we have a formula for a partial sum. It's going to be n, which is 60 in this case, divided by 2, times our first term, which is 8, plus our nth term, in this case our 60th term, which is 185. And so if we simplify all of this down, that's going to give us our sum. And again, we expect a pretty big positive number because we're adding up increasingly large positive numbers. So 60 divided by 2 times 8 plus 185. And that's going to give us 5,790. Okay. So now that we've had some practice evaluating these sums, let's look at another application problem. So an application problem that involves some type of finite arithmetic series. Okay, so suppose that a job offer offers a starting salary of $75,000 with a raise of $4,000 each year thereafter. We want to write an expression for the nth term of the arithmetic sequence that represents this salary as a function of the number of years of employment. And then we want to find the total income, everything that an employee has made, who works at this job for 20 years. Okay, so how do we know that an arithmetic sequence is going to apply? Well, it's based on how this job offer is structured. So we have a starting salary of $75,000. Think of that as the first term in the sequence representing the values of the salary. And then we get a consistent raise of $4,000 every year. So every year thereafter, add on $4,000 to the 75 and then keep going from there. So this is going to be our common difference. So based on that, we can write the nth term, and the nth term is going to represent the total salary we make in a particular year. So a sub n in this case is going to be a sub 1, which is $75,000, plus n minus 1, where n is the number of years, times $4,000. Okay. So now this being said, let's think about this. Let's think about this for just a moment. We're starting at 75,000. Okay, so that's where we start. But are we talking about the n number of years as in a year has elapsed? Are we talking about starting at 75,000 as in the first year it's 75, or a sub 0 would be 75? There's different ways to interpret something like this. So we're going to assume that a sub 1 is 75,000. The first year of employment, n is the first year of employment, we have 75,000. Now there's slightly different ways to interpret this kind of problem. If we're thinking of n as the number of years that have elapsed, well, if we start with 75,000, then when 1 year elapses, we would add on 4 and we would get to 79,000. So we could also kind of interpret this problem with a different value of a sub 1. Potentially we could think of a sub 1 as being equal to 79,000, what we get after the first year. It really depends, and that's kind of open to interpretation right here. But what we're really focused on is just the structure of the problem, where we start and then adding on the 4,000 thereafter. Okay, so for the first year we make 75,000, and then each year thereafter we add on 4,000. So just keep in mind with these kind of applied situations, there are potentially some variations with how we can interpret these values. Okay, so now that we know this, we have our nth term that represents our salary in a particular year. We want to find the total income for an employee who works for 20 years. So in other words, we want the 20th partial sum based on a sequence defined in this particular manner. So that's going to be 20 divided by 2 times the first salary plus the 20th salary. So we're going to work under the assumption that $75,000 is our A sub 1. So we need the 20th salary then. After 20 years, we've gotten that many raises. How much money are we making after we've continued to add on that raise of $4,000? Well, A sub 20 is going to be 75,000 plus 20 minus 1 times 4,000. Okay, so 75,000 plus 20 minus 1 times 4,000. And that's going to take us to 151,000. Okay. So once we've worked for this company for 20 years, assuming that we've continued to get a $4,000 raise every year, this will be the salary that this person makes. So we're going to sub in those values, where we start and where we end after 20 years, to our partial sum formula. So 20 divided by 2, I'll go ahead and simplify that. That's going to be 10. And we're taking 75,000, starting salary, plus the ending salary of 151,000. And we're going to simplify all of that. So 10 times 75,000 plus 151,000. And there we go. So be careful with your zeros. Write all of that down and then determine where your commas go. So 2, 2, 6. And then it looks like we have 4 zeros, so 1, 2, 3, 4. And you always start at the end, smallest place value, and add in your your commas and threes. So there we go. And we're talking about a dollar amount, so that's going to be $2,260,000. That's the sum of the annual salaries if we start at $75,000 and get a $4,000 raise. After 20 years, this is the total amount of salary. So just to summarize, what do we now know? We know what an arithmetic sequence is. We've had a lot of practice generating the nth term, which is going to be one of the most important things we do when we're focused on this kind of sequence. Based on understanding the structure for this kind of sequence, we can determine a lot of different unknown types of things. We can also add up a finite number of terms in an arithmetic sequence, and we've also looked at a few examples where we do that.